At the end of class on Friday, everybody, we were working on this problem. I wanted to back up and go back over some of the choices that we made in this problem so you're comfortable with it, and then show you some of the algebra that we would use to solve it. I thought that might be a good use of our time outside of class. We'll regroup on Monday to make sure everybody's comfortable, but this is going to help you get prepared for Monday's class. So when we have a chemical reaction, and we have reversible arrows, that means that we now often need to kind of get our perspective or our bearings in order to understand which way the reaction is going. And so we talked about calculating the reaction quotient on Friday. And so I want to take you through that again. The reaction quotient is calculated just like an equilibrium expression is written, except it's a number that we then compare to the size of K. So let's look at how to do that here. We're going to write products over reactants for this reaction, okay? And we're going to plug in the numbers that are given in the problem. We haven't found equilibrium concentrations yet. We just have initial concentrations. So Q is kind of like a compass where we're going to calculate what it is and tell us, is it pointing us towards K where we need to get bigger and go right? Or have we overshot K, we're too big as a Q value and we need to go left? This is a real extreme example. See how we have all products and no reactants? That's because this essentially is a reaction that is shown backwards, okay? Where we are looking at it from left to right, but really it's going right to left. And because we're oriented left to right the way we write things, it's awfully hard to see this. So because Q is so much greater than K, we actually tend to just flip the reaction around. So we're going to write this reaction reverse from what it's shown right here. And remember, we have a trick for what to do with the K value when that happens. So don't forget that. So we did this in class together. One thing I want to make sure I define for you is that we let X equal the amount of product formed. We can let X equal the amount of anything. That's just what we decided to call it here. So see how we're starting with a number under the reactant, right? We have 0.025 molar under NO2. That's what we were given in the problem, but I'm showing it on the left-hand side of this reaction. That's because when we lose on the left, we can set up our ice chart the way we're used to. We're going to gain on the right because products are positive. Remember, we talked about stoichiometry and how that influences how many X's you lose or gain. The trick to ice tables is to always use the column information from the initial and change rows, add those up, and that's how you get the equilibrium. So 0.025 plus a negative 2x gives us 0.025 minus 2x. Try it again. 0 plus a positive x gives us x. So ice tables really help us organize our variables, essentially. So the trick next is to figure out the equilibrium concentrations of these molecules. And to find equilibrium concentrations, we need to write an equilibrium expression. The equilibrium expression for this reaction is going to be products over reactants. Now, look what I've done to K. I've called it K prime. Why do you think that is? The K that was given was for the reaction that was reversed from this. So I'm calling this K a new K because I'm going to end up having a different K than what I was given. What I'm plugging in is product over reactants. Okay, it looks like I forgot my little brackets on the N2O4 here. Sorry about that. That's a concentration also. So I'm plugging in the equilibrium row number for N2O4 over the equilibrium row number for 0.025 minus 2x, for the 2 and O2. So this 2 is showing up a lot, right? This 2 right here means I have a 2 right here. It also means I have a 2 right here. So those coefficients really make a difference. It almost feels like you're double counting them, but you're not. I just don't want you to forget to use them in two different cases. So how do we find an equilibrium constant for a reaction that's reversed from one that we knew already? Do you remember that? We're going to invert the K. So K prime, our new K, we can call it whatever we want, our new K is 1 over the 0.36 number that we were given initially. So now you've got all the ingredients to be able to solve this problem. What may be causing you some anxiety is the math. So let me make sure that you're comfortable with that. I'll take you through some steps. This is more in depth than I would normally do in a classroom setting. So I've got my K, which is the inverse of the K I was given, and I've got my equilibrium expression, which I wrote for my reaction. So my job now is to try to simplify and get everything kind of sorted out. So I can see from my squared term that I'm going to end up having a quadratic formula, or a quadratic equation, I should say. So I'm going to cross multiply. Everybody see how that was done? I'm going to cross multiply 0.025 minus 2x whole quantity squared equals 0.36x. All right. Next thing I need to do is FOIL. Review your ways for expanding these terms so that you can remember how to get everybody, all your different linear x and x squared terms. And then I'm going to group everybody by the terms. For a quadratic equation, we need to get everybody on one side and a 0 on the other. And remember, when you go to use the quadratic formula, you're taking out your coefficients a, b, and c. Pause the video for a second and see if you can remember how to set up a quadratic formula. Okay, so I hope you paused the video and maybe tried a little bit on your own there. Let me walk you through how to solve this. Remember, x equals negative b plus or minus the square root of b squared minus 4ac over 2a. That's a mouthful, I know. It'll come back to you if you haven't seen it in a while. You're going to practice using it a lot in chapters 14 and 15. Remember, you're going to get two roots a lot of the time. How do you choose the right root? There's only going to be one right answer. You need to choose the answer that doesn't give you kind of a meaningless concentration. So here, remember, we're going to subtract x, double x, from the original 0.025 molar. So it couldn't be the 1136 number. That would give us a negative NO2 concentration, which we can't have. So that means it's the root in the red box that is going to be the correct root to use. Don't forget, the point of doing all of this math was to find x. X represents the amount of N2O4 we produced. It also represents, when we double it and subtract it from 0.025, the amount of NO2 left. So I hope this helps you walk through A, why we reverse the reaction in order to do the equilibrium concentration calculation, and B, it gave you a little primer or review on how to deal with quadratic equations and how to evaluate what roots are appropriate. Keep in mind that we're going to go over some shortcuts to this on Monday so that we're not completely drowning in math all the time. So make sure to come on Monday so we can talk about that together. Thanks so much. Take care.